Rotational angular momentum, you can change both the magnitude and the sense of rotation, right? The projection of that rotation. Same is true for orbital angular momentum. For spin, that's not the case.
Go.
For spin, the spin of a particle is a property of the particle, right? All photons have a spin of 1. All electrons have a spin of 1/2. You can't change the spin of an electron. You can change its projection. Is it up or down? But you can't change that it's spin 1/2. A Higgs boson, the famous Higgs boson, has a spin of 0. If you change the spin of the particle, you change the particle, right? Just like the mass of a particle is an intrinsic property of the particle, just like the charge on a particle is an intrinsic property of the particle, so too is spin. That's different than the other angular momenta we were talking about. What's the same is that the commutation rules are still the same. You can only specify one component of spin and its magnitude at the same time, and you can't specify any two components at the same time. Similarly, the eigenvalue algebra is all the same. The magnitude part, you still get a s times s plus 1. The component part, the projection part, you get an m sub s, right? So now we're going to have s and m sub s values. You can't change s without changing the particle, but you can change n sub s. You can change the projection of spin. Where does that come from, right? Okay, the same commutation rules and eigenvalue. It's because it's an angular momentum of a sort, right? Now it's a much different angular momentum, right? In quantum mechanics, we showed that for orbital angular momentum, rotational angular momentum, right? We had some function of the spatial coordinates, r, theta, and phi, right? Spin, it turns out, is not a function of the spatial coordinates. It's an intrinsic property of the particles. Spin, right now, we're just sort of adding on spin. What we'll have to do is solve the Dirac equation, which is a relativistic equation in which time is treated as an equal coordinate, just like the other spatial ones, right? You get a 4 space. Because of that, we can't write functions for the spin in terms of the spatial variables. So we're just going to call it, we've got a state, say a ket, right? That has an s and an m sub s value. If it's an electron, the s value is always 1/2. You can either point spin up or spin down, m sub s plus or minus, but we can't write that as a spatial function anymore. So we can just write it as, say, a ket. We can call it something like an up state or a down state. And so sometimes we'll just represent that by an arrow, an up arrow or a down arrow. Or sometimes it's simply represented by alpha or beta, a Greek letter, right? You can't write a function, but we can symbolically represent what the spin is, right? We can't write a function of spatial coordinates because the spin, an extra quantum number, only comes about from quantization in the 4th dimension. That's what we're going to do with the Dirac equation later on. Okay? Because the spin is an intrinsic property of particles, it also means that it classifies the particle. And there are 2 big classifications. We've encountered these before. Now we see where it really is coming from here, right? This half integer spin, call those particles fermions. Pauli exclusion principle depends on, right? That you can have for an electron, for example, right? You have the same value s, but different values of m sub s, and therefore no more than 2 fermions, electron being our prototypical fermion, no more than 2 can go into any one state. Integer spin particles are bosons. They act much differently. The photon is a boson. We can put as many photons in a state as we like. They don't interact with each other strongly, right? And therefore they have different counting statistics. all right? Or they have a much different way of interacting with each other than fermions do. Fermions, you're only allowed to put 2 in the state. Bosons, you can put as many as you like in a state. Bosons have integer spins. Fermions have half integer spins, right? So the Higgs boson, integer, W boson, Z boson, right? All of these are bosons because they have integer spin, whereas electron, muon, neutron, they have half integer spin. Proton, of course, proton, very important. That's where NMR comes from, right? The half integer spin there. These have different counting statistics than particles with integer spin. There are some particles, nuclei, that are composite particles, right? Nuclei have combinations of neutrons and protons, so they have a spin as well that comes about because they're composite particles that have spins. You can change the spin of a composite particle. So the nucleus and nuclei can have their spin change sometimes, but you can't change elementary particles. You can't change their spin. Very rapidly is our introduction to angular momentum. All angular momentum obey the same eigenvalue equations, the same eigenvalue algebra. Magnitude squared equals J times J plus 1. H bar squared would be our units, right? Projection M sub J times H bar. We're eventually going to quantize a system, the hydrogen atom, in 4 dimensions, the 3 spatial plus time, and that's where the spin is going to come out naturally. It won't just be bolted on, but once we do the Dirac equation, quantization along that 4th axis will give us a 4th quantum number, S, the spin. Spin is a little bit different from the other angular momentum in that it's an intrinsic property of elementary particles. You can't change the spin of a particle without changing the particles. It is not a function of the spatial coordinates. It comes from quantization along the time axis.